Let us solve few numerical. You can read the question from your screen. In the question, we are given with volume charge density, rho V, and we are asked to find the total charge that is contained by the volume that is given in the question. My dear, before solving the question, first of all, carefully observe how volume is represented in the question. We have seen that for the representation of the volume, we have all three coordinates variables, isn't it? And you can observe the same thing from the question also. We are given with the ranges or limits for all three coordinates. That means all three coordinates are variables, isn't it? You can also observe that we are given with the ranges or limits for the variables rho, phi and z. That means this question belongs to cylindrical coordinate system. We are going to solve this question with the formulas that are used for cylindrical coordinates, isn't it? But hold on a second, my dear. Carefully observe the given function rho v. It is in terms of x, y and z. That means it is represented in Cartesian coordinate system. But just now we have concluded that we are going to solve this question in cylindrical coordinates. So now there is a problem. The given function is in Cartesian coordinates. The ranges for the integration are in other coordinates, cylindrical coordinates. So what should we do now? My dear, it is very simple. We have to bring both of them into the single coordinate system. So what I am trying to convince you that though the given function rho v is in Cartesian coordinates, we will convert it from Cartesian to cylindrical coordinates. We can also do one thing. We can convert the given limits into Cartesian coordinate system and solve the question in Cartesian rather than in cylindrical. But I wouldn't recommend this approach because of the complexity involved. So by the simple way, let us just convert the given function, the given charge density from Cartesian to cylindrical. Now remember the lectures of coordinate systems. We know that in Cartesian we have the variables x, y and z. Cylindrical is defined by rho, phi and z. And we also know the interconnection between them, isn't it? It is like x equal to rho cos phi, y equal to rho sin phi and z equal to z, isn't it? So by putting x, y, z, we can convert the given function from Cartesian to cylindrical, as you can see from your screen. Now we are given with the volume charge density rho v, and we are asked to find the total charge that is contained within the given volume. My dear, we have discussed about the charge densities in previous lectures. Volume charge density is nothing but the total charge per unit total volume within which it is deposited. So the total charge will be given by like this: volume charge density into the given volume. But we have to find this total charge by the use of integration. And the total charge will be given like this: volume integration of rho v. My dear, can you guess why? Why we have to make the use of integration? Just remember the previous lectures where we have discussed about the charge densities. Whenever there is an involvement of function and we have to find the total value of the function over certain range, then we have to make the use of integration, isn't it? So to find the total charge, we have to solve this integration, volume integration of rho v. Now we are given with the rho v, the volume charge density. We have already converted it into the cylindrical coordinates. Now let us write the dv, differential volume. We are solving this question in cylindrical coordinates. So the differential volume dv will also be required in the cylindrical coordinates. Now my dear, just remember, how do we write the differential volume? My dear, we write the dv, differential volume, from the expression of dl, isn't it? So just recall the dl for the cylindrical coordinates. It is like this: Just skip the unit vectors, multiply all three coefficients, and our differential volume dV will be rho d rho d phi dz. So let us put rho v, let us put dV, and our integration will like this. Now my dear, we have represented the line integration by single integration, because for the given line only one coordinate was variable. Similarly, for the surface integration we have used double integration, because for the given surface out of three, two coordinates are varying simultaneously. Now here we are talking about the volume integration, and we know that for the volume all three coordinates are variables. So what I am trying to say you, line integration was the single integration, surface integration is the double integration, and similarly the volume integration will be the triple integration. That means we will have the limits for all three variables. In our question, we will have the limits for rho, phi and z, because we are solving the question in cylindrical coordinates. And the limits for rho, phi and z are already given in the question. You can carefully observe that from the question. We can put that limit into our integration, and the integration would become like this. This type of integration we already know that called as variable separable forms, and this can be very easily solved by the knowledge of mathematics, and by solving this integration we can conclude to our final answer, or we can conclude to our final charge, as you can see from your screen. Let us take one more numerical. You can read the question from your screen. We are given with the rho v, volume charge density in the question, and we are supposed to find the total charge that is contained by the complete universe, right? Now my dear, by now you are very much familiar how to find the total charge using charge densities, isn't it? We are supposed to find the total charge. That means we will be solving this integration, volume integration rho v dv. Am I right? Now, my dear, in this question, we are asked to find the total charge that is contained by the complete universe. So, we can easily use the spherical coordinate system to solve this question. Indirectly, in this question, we are given with the ranges, the limits for the spherical variables. Remember the spherical coordinate system. Spherical coordinate system is defined by r, theta and phi. Am I right? So indirectly in this question we are given with the ranges of r, theta and phi. My dear, we are talking about the universe. We are talking about the earth in this question. So of course the range for the variables, the limits for the variables, we have to take the limits of the variables at maximum. Am I right? We have to take the limits of each variable at their maximum values. For example, remember the r. R can take value from 0 to maximum infinity, isn't it? So the limits for r will be 0 to infinity. Remember the theta. Theta can take value between 0 to pi by 2. So the range for the theta will be 0 to pi by 2. Similarly, phi can take any value between 0 to 2 pi. So its range will be from 0 to 2 pi. So what I am trying to say, in this question we are indirectly given with the limits. We are supposed to find the total charge within the universe. That means within the range r 0 to infinity, theta 0 to pi by 2 and phi 0 to 2 pi. So already we are given with rho v. We are now ready with limits also of r, theta and phi. Now let us write the dV, the differential volume. Now my dear, you already know how to write the dV. We write the dV from the expression of dl, isn't it? So just recall the dl, differential length, For the spherical coordinates, it is as like this, as you can see from the screen. Just skip the unit vectors, multiply all three coefficients together, so we will get our dv. It is r square sine theta dr d theta d phi, isn't it? So putting everything together, our integration will become like this. Put limits properly, separate each variable properly, you will come to know this integration is nothing but the variable separable form that we have solved many times before. So this integration can be easily solved with the knowledge of mathematics, and we can conclude to our final answer, the final charge, as you can see from the screen.